Hello everyone, welcome to my video lecture. Today I came up with the application of Laplace transformation. Laplace transformation, how we apply while we study Laplace transformation in mathematics, or the application of Laplace transformation can also apply in any other discipline outside the mathematics, but today we solely focus how Laplace transformation applies in differential equation generally. Last time we have been discussed about the Laplace transformation on certain function and the inverse Laplace transformation, the basic property, so that today it will not be difficult to you if you are going to apply the Laplace transformation, because much of our discussion are involved with the previous discussion, but clearly it's not a little limited with the application. The main application in mathematics is solving ODEs with IVP and solving the system of differential equations. We solve an ODE with IVP using Laplace transformation. Again, we solve systems of differential equation. Again, we use the system of differential equation, especially the IVP system, and we apply the Laplace transformation in solving the differential equation rather than the techniques you have been addressing in the previous and higher order differential equation, second order, first order. You have seen methods, but rather than this method, we can apply in a simple form using Laplace transformation. So there is a technique how we apply Laplace transformation. This is the framework to apply the Laplace transformation. A rule in finding solution of differential equation using Laplace transformation. The first thing is apply Laplace transformation of the given equation. We take Laplace transformation both sides of the equation, that means term-wise Laplace transformation. Every term should be transformed to the new form of equation, so that in step 2 we solve for the unknown transformed function. So in step 1, while you are applying Laplace transformation of individual term, the equation turn it or transform it into algebraic equation, so that we create a new system of algebraic equation or any form, so that we solve for the unknown transformed function. We solve for the unknown transformed function. The third step is apply inverse Laplace transformation for the unknown transformed function. Once we get or obtain unknown transformed function, then we apply inverse Laplace transformation. Then finally you solve for the unknown function using inverse Laplace transformation. We apply transformation. We will do it through instance. We develop the idea with the instance so that it will be clear to you. Now let's say we have examples here. Examples solve the following IVP via Laplace transform, where a is y double prime plus 4y prime plus 6y equals to 1 plus a raised minus t. Then y at 0 is y prime at 0 is again 0. This is the second order differential equation is constant coefficient, non-homogeneous, actually non-homogeneous because of this term. Again, the second one is also non-homogeneous. Clearly, you have seen two methods of solving the non-homogeneous DE: the method of undetermined quotient and method of variational parameter. In method of undetermined coefficient, it has a limitation. especially for trigonometric function, exponential function, and power function, polynomial function. It works, but it doesn't work for natural logarithm, for tan, or any forms other than I have already mentioned it before. So that due to its restriction, we pause to the method of undetermined variation of parameter. It works for any differential equation either with constant coefficient or with variable coefficient in a non-homogeneous aspect. But this Laplace transformation, application of Laplace transformation, is essential in nature to find a solution of the differential equation. So let's carry on our discussion based on the rules that we have mentioned before. So in solving A will be, we will look at A, then B is as an exercise. They have to be, I will give you a clue. Now in A, we make Laplace transformation. Each individual term should be transformed. That's here, Laplace transformation of individual. That means Laplace sign of y dot prime equals Laplace sign of this. Both sides we apply Laplace transform this operator. That means individual term is transformed Laplace sign of y dot prime for y prime. We use the linearity property that the constant can be moved out. So that 4 Laplace sign of y prime plus 6 Laplace sign of y then equals Laplace sign of 1 plus Laplace sign of e raised minus t we may. Now to apply this, we remember again the property of Laplace transformation. Laplace sign on derivative, remember that Laplace sign of f prime of t mean as f of s minus f of 0. Again, Laplace sign of f double prime of t is s square f of s minus s f of 0 minus f prime of 0. This is obviously derived from the comprehensive definition. You can extend it to a much more high derivative or Laplace sum of the derivative. Now, using this idea, we form Laplacian of here. Okay, Laplacian of this we mean s square y of s. Okay, this is, let me start it here. We will work out. All right, good. So s square ys minus, using the Laplace for derivative we got here for y dot prime. For y dot prime, this is, let me, I think it's better to write this. Good. Oh, wow. All right. So Laplace of y dot prime, we mean using the derivative which I have already showed you before using this formula. Okay. So we have here plus, for this again we have this. Again, for the other one is 6 Laplacian is 6y of s. Again, for Laplacian of 1 plus Laplacian of 1 plus Laplacian of 1 is 1 over s. Laplacian of 1 e raised minus is this here. Now keep this in mind. Now go to the second slide. So we have this s square y of s. Again, we use the initial condition already mentioned before, given. So we get this form. Then we move out. Y of s is common. Y of s is here. S square 4s plus 6. So 1 over s plus this. Or in simple form, we have 2s plus 1 over s into s plus 1 we may. So y of s is this. We have completed the second step in that is solving the unknown transformed function. Where the unknown transformed function is here. We have to apply or play the inverting rule. That means applying inverse Laplace transformation. So to do this, we have to make the partial fraction decomposition here. For the second one, especially for this, is we use the partial fraction decomposition for any this 2s plus 1 we have this partial fraction decomposition form. Okay, so we need to be determined the unknown coefficient, constants a, b, c, and d. So for this, we have this form. We get this equation because of here. Okay, because of this, we just find out a, b, c, and d, so that ultimately we get y of s is here. That's the new transformed function. Partial fraction decomposition, I think we have already familiarized with that. Finally, after we have y of s is this, so we need to apply inverse Laplace transformation, or possibly this is the this denominator here is, look at for the denominator this is a quadratic form, the mean and irreducible, which means b square minus 4ac is less than 0. For irreducible, we use complete square method. For any x squared plus bx plus c, we have this completing square method. Using that, we have to be rearranged to the form of here. Okay, y of s is this. So that was the first one, is this, so that it can be turned to this form using the complete square method of here. Now we just make to shift this based on the denominator. I think we have already seen in inverse Laplace transformation how we compute the Laplace transformation, inverse of Laplace transformation. So y of s to the simplest form is here. We apply inverse Laplace transformation, Laplace inverse of this, Laplace inverse of this, here and here. Individual terms should be also returned back. The reverse processing. So Laplace inverse of y of s is y of t, 1 over 6, the constant can be moved out using the property, linearity property, because inverse Laplace transformation can have also a linearity property. Due to that, we have 1 over 6, 1 over 3, Laplace inverse of 1 over s plus 1, minus 1 over 2, Laplace inverse of s plus 2 of here, again minus 2 over 3 is this. So 1 over s Laplace is 1, so 1 over 6 times 1, again 1 over s plus 1, it is inverse Laplace transformation is e raised minus t. Again, this is, we ignore the shift for the time being, so for s over s plus, we mean here, we have this form, Laplace inverse of s over s squared plus s squared is equals to t, again Laplace inverse of 1 over s squared plus s squared is here. So with that formula, we get this minus, just shifted, ignore the shift, that means s over s squared is cos square root of 2t, a in this case is root 2, that's why squaring means 2 here. Then shifting toward this minus 2 mean we multiply the original function by e raised minus 2t, that's similar with here. So thank you.